Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. Imagine a city planner with no brain, no degrees, and no consciousness, yet capable of designing the optimal transport network faster and more efficiently than any team of human engineers. This isn't science fiction, it's biology, and its name is Physarum polycephalum asterisk, the incredible yellow slime mold. To understand the significance of this creature, we must first appreciate the complexity of building a transport network. Whether it's rail lines, highways, or fiber optic cables, engineers face a crucial, frustrating dilemma: balancing cost versus resilience. You want the shortest possible paths, low cost, but you also need redundancy so the whole system doesn't collapse if one segment fails, high resilience. In 2010, Japanese scientists took on one of the most elaborate and confusing transport systems on the planet: the Tokyo Metropolitan Rail Network. Their goal wasn't to map it with computers, but with mold. They placed oat flakes, the slime mold's favorite food, in a pattern corresponding to the major urban centers around Tokyo. Then, they introduced a single blob of Physarum polycephalum. What happened next was astounding. The slime mold, which is essentially one giant cell spanning several square feet, began to explore. It extended protoplasmic tubes across the agar plate, searching for the food sources. Within 26 hours, the slime mold had not only connected all the cities, but had done so using a pattern strikingly similar to the actual, optimized Tokyo rail system designed over decades by human engineers. It achieved optimal balance, minimizing the total path length, cost, while maintaining a high degree of connectivity and fault tolerance, robustness. But how does an organism with no central nervous system perform such complex computations? The answer lies in decentralized biological algorithms based on simple, powerful physics. The slime mold operates on a continuous loop of positive and negative feedback. When a protoplasmic tube finds a rich food source, or successfully connects two food sources, the flow of nutrients through that tube increases. This flow causes the tube walls to thicken and stabilize, a process known as reinforcement. This is the positive feedback loop. Success breeds permanence. Conversely, if a path is inefficient, meaning the nutrient flow is low, or the path is excessively long and redundant, the tube diameter shrinks and eventually dissolves completely. This is the negative feedback loop. Inefficiency leads to elimination. This simple mechanism is running in parallel across the entire organism simultaneously. Every point on the slime mold is constantly assessing its local environment and making tiny, localized decisions about thickening or thinning its structure. This parallel processing capability is what allows it to quickly converge on a global optimum that satisfies those competing requirements of cost and robustness. Think about the engineering challenge again. If an engineer maximizes robustness, they create a dense, highly redundant mesh, expensive and inefficient. If they maximize efficiency, they create a few simple, direct lines, cheap, but prone to catastrophic failure. Physarum finds the sweet spot, the Pareto optimal frontier, naturally. Researchers have since tested the slime mold against even more complex scenarios, including mapping global airline routes and designing theoretical computer chips. In almost every case, the biological algorithm either matches the efficiency of the best human-designed systems or, in some instances, outperforms them by finding novel, unexpected solutions. The implications for future technology are immense. Scientists are developing slime mold algorithms, computational models based on Physarum's asterisk logic, to solve problems like optimizing evacuation routes during disasters, designing resilient power grids, and creating new, adaptive forms of machine learning. Instead of relying on rigid, top-down blueprints, We are learning to build systems that self-organize, adapt, and heal, mirroring the intelligence encoded in the simplest forms of life. The slime mold, a seemingly primitive creature, proves that complexity doesn't require consciousness. It requires elegant, decentralized rules. For more incredible facts like this, don't forget to subscribe and turn on notifications.